Hello everyone. In today's class, what we're going to do is review the homework assignment from yesterday. Now, if you did not complete it, you will not be marked present for yesterday's class. Please be aware, if I ask you to do it, you don't have to comment on the video. What you have to do is complete the homework assignment. So this is the homework assignment that was given yesterday. Let's look at it together. First thing we're going to do is we're going to read the question carefully, try to determine the objective function, as well as looking at the constraints governing our decision. So, Singer Cola is one of the most successful cola companies in Asia. The first Singer Cola was produced in 1933, and since then, it has been exported to 50 countries worldwide. All of this, while interesting, does not in any way affect our situation. So for right now, we can largely ignore that. Moving on, the cola is still a top seller in Thailand. And one of its main distribution centers, a manager has been presented with a linear programming problem. Let's divide that right now. Because again, while this is interesting, and it does explain how these questions can happen in real life, it's not necessarily something that we have to consider strongly right now. Moving on. One of the Singer factories in the northern part of Bangkok supplies 4 different villages from 3 of its plants. So here we have our first critical piece of information. We know, and now of course we know because this is themed homework, but if we weren't aware, if we didn't know that this was a management science based on transportation, now we do. So let's highlight that key point. And the unit cost of each box is presented in the table below. So here we have our unit cost, just like we saw in the question I did yesterday. So now we have 3 key pieces of information. 4 different small villages, 3 of its plants. Plant A, B, C, city A, B, C, and D. And we have the shipping costs for each of those. So what we can do now, and we're going to, just for simplicity's sake, is we can begin putting together our objective function. Generally, to see if it's a shipping problem, we're trying to minimize cost. So unless this changes, for now, we'll make it minimize z, where z represents shipping costs, is equal to x1, 1a plus x1b plus x1c plus x1d plus x2a plus x2b plus x2c plus x2d plus x3a plus x3b plus x3c plus x3d. Now, in this situation, we have our shipments from plant A, our shipments from plant A, plus our shipments from plant B, plus our shipments from plant C. So what we'll do is we'll move this down just to make it a little easier to understand. So minimize z. shipping costs. And this isn't necessary, but it might help us see our situation a little bit more clearly. This is ship plant A plus ship plant B plus ship plant C. That's what we've shown. We're showing that our minimization, we're attempting to minimize our shipping costs with all the shipments from plant A to villages A, B, C, and D, plus our plus our shipments from plant B to cities A, B, C, and D, plus our shipments from plant C. And that's cities A, B, C, and D. Now, once we've put together our objective function, and that's what we've done here, we'll make all of this bold because that's a critical piece of information. Okay. Now, what we're going to attempt to do now, not what we're going to attempt, but what we're going to do now, is now we're going to list our constraints. We begin with C1. But before we can do that, we have to go in and we have to look at our question again. So let's continue on with our question. There are other constraints that need to be considered when formulating the linear programming problem. Not all plants are able to supply the same quantity of cola required. So this information is essentially telling us it's very similar to the problem we answered last time. However, last time they gave it to us in a chart form and it was very easy to see. Today, it's given to us in natural language in a paragraph. So it may be a little more challenging. We might have to be a little bit more careful. So let's continue. According to the last estimation, plant A can supply a maximum of 35 per day. Let's highlight this because that seems very important. Now, if plant A can supply 35 per day, that means they can ship 35 units per day. That's our first constraint. So, looking at plant A can ship to X1A, and that's our shipments here, city and plan, X1A, plus X1B, and that's up here, 1B, plus X1C, right here, plus X1D. And this is, or we know they can supply a maximum of 35 per day. So this must be less than or equal to 35. This gives us our first constraint. The total number of products shipped to city A, city B, city C, and city D from plant 1 must be less than or equal to 35. We do the same again, C2. We go back to our problem. Plant B can supply 50. Also important. So we go here, X x2a plus x2b plus x3 x2c plus x3 x2d is less than or equal to 50 units. That's what we've seen. Everything shipped from plant B, number 2, must total less than or equal to 50. That's all they can produce. So we go down, we do number 3. And we see here plant C can supply 40. Okay, so we come over here, x3a plus x3b plus x3c plus x3d is less than or equal to 40, which is their level of supply. So we've completed the first section of our transportation problem. The constraints dictate how much can be shipped from each of the 3 plants, each of the 3 factories. For each factory, we can only ship that amount. They cannot produce any more, so we cannot ship anymore. That's what we've indicated here. Moving on, down to C4. We see here our requirements. City A needs at least 45 each day. City B needs 20. Cities C and City D need 30 to fulfill demand. So we have 4 more constraints. We have C4, C5, C6, and C7. Moving up here, we see that City A needs at least 45 each day. So City A is right here. City A can receive shipments from 1A, 2A, 3A. So we see here x1A plus x2A plus x3A must be greater than or equal to. Now, in the last problem, we saw that they needed an exact amount. That's not the case this time. And this time, they need at least 45 each day, at least 20, at least 30 for C and D. So it must be greater than or equal to, in this situation, 45. We'll repeat that here. X City B is X1B, 2B, 3B. Must be greater than or equal to 20. One more time. X1C plus X2C plus X3C greater than or equal to 30. And the last one, X1D plus X2D plus X3D is greater than or equal to 30 again. So right here, what we've done to begin this question is we've put together our objective function and the constraints governing our decisions. We've shown that in this scenario, it's very similar to what we saw before, but the information, instead of being given to us in chart format, required us to interpret in natural language into our constraints because it wasn't immediately clear right away. Now, one thing is different. When we put this together, this number x, I kept it simple here, but we can also remember the number x. We can replace the number x with the data given to us in this chart here. For now, it's not very necessary because we will work together in the next section when we solve this problem in Microsoft Excel. So thank you for listening to section A. We'll be back in a couple, well, you'll be back immediately. For me, it'll be a couple minutes, and I'll see you in section 2. Thank you for listening. Hello, everyone, and welcome back to section 2. In this section, like we did yesterday, I'm going to solve the homework problem for you using Excel. The reason I'm using Excel instead of QM is because at this level, it's quite a bit simpler to use QM. So we want to focus on the more difficult one because if you can do this, QM should be quite easy for you. So let's begin. We're going to, as always, call it a very simple transportation homework example. So we go right here, and like we did last time, we're going to, instead of using the base idea, x1a, x1b, we're going to add in our actual titles because it helps us a little bit better understand what's happening. So we're going to call this shipping routes. The first route is plant A to city. And that's quite simply what we're doing. We're talking about the driving from plant A to city A. Next, we go with plant B to city, plant A to city. Plant A to city C. Oh, plant A, city B. And these are all our shipments from plant A to the various different cities. So now we move to plant B. And we've seen here in these four, F, G, H, and I, those are all of our shipments from plant B to city. Each of these represent a shipment from our second plant to one of us or to our four destinations. Continue on with the last four plant, and these represent all of the shipments from plant C that was silly. Okay, so So these four in this section represent our four shipments from each of the four, from plant C to each of the four cities. What we've done here is we've labeled each section of our objective function. As we can see down here, instead of x1a, x1b, x1c, x1d, we have plant A, city A, plant A, city B, plant A, city C, plant A, city D. Both are acceptable, both are totally okay, but for comprehension, labeling them is probably the better choice. So what we're going to do now is we're going to enter our values for our objective function. We see that in our objective function, we're trying to minimize cost. So to do that, this is what we do. We're at 8, 6, 10, and 9. We see that right here. Plant A to city A, plant A to city B, plant A to city C, plant A to city D. We continue with 4, 8, 12, and 9. And that's right here. B to A, 2 to A, 2 to B, 2 to C, 2 to D, or plant B to A, plant B to B, and that's what we've seen here. In the last section, okay, so we've completed our objective function. That's the same thing we always do. Once we've done that, then we move on to our constraints or requirements. That's where we fill in right here. The first one, constraint 1, is the maximum supply plant A. Second one, we see that here. Plant A can supply a maximum of 35 per day. The next one is max supply plant B. Right here, B can supply 50. Max supply plant C. Once again, 1, 2, 3 right here. Now, we also have 4 more. The first one is city A requirement. City B requirements. City C requirements. City D requirements. So what we've outlined here is our okay. Try it the other way. What we've outlined here is our objective function, and what we've outlined here is our constraints. So we didn't do it this way last time, but we can do it this way this time. It doesn't matter. So we have x1a, which is plant A to city. I see what happened. Okay, I clicked on the wrong thing. So here we have x1a, which is city A, x1b, plant A to city B, x1c, plant A to city C, and x1d, plant A to city D, must be less than or equal to the 35 they can produce. That's what we've done here. So we'll label this constraint supply. We do the same thing here. We know that X2A, which is plant B to city A, plant B to city B, plant B to city C, plant B to city D, must be less than or equal to 50, because that's how they manufacture. And the last one, maximum supply at plant C, 1, 1, 1, 1, must be less than or equal to 40. That's how many they produce at plant C. So our first three constraints are taken care of. Let's go down a little bit here on our page to our less form. So x1a, which is right here, plus x2a right here, x3a must be, in this situation, greater than or equal to 45, meaning the goods shipped from plant A to city A, plant B to city A, and plant C to city A must be more than 30, 40, 45, because that's what they require. We repeat again here. Greater than or equal to 20. The last two, we can continue the same pattern. The last one, right here. So what we've shown is that our constraints are now fully accounted for. And again, it doesn't matter what order we do this in. So we're going to, instead of moving down here like we usually do, we'll do it up here because it doesn't really matter. So we have to enter our usage formula. And that is the number of times we leave plant A. Let's skip that for now. It'll be easier, I guess, to visualize. So let's go down here. And this is what the computer will attempt to tell us. The computer will run permutations of this to find our optimal solution. So plant A, city A, plant A, B, plant A, C, plant C. Repeat again for plant B. One more time for plant C. So what we've indicated here is all of our shipping routes. And we're trying to minimize our shipping costs. So that goes down. So now that we have this information, we can now move up here. So to figure out our total cost from shipping route A to city A, we go here. So let's do our total usage over here. Now we've completed using this. So for now, I'll close it and I'll go full screen just so it's a little easier to see. Okay, so We'll minimize some of our columns to make things a little more clear. Once we get everything on the same page, hopefully it'll be a little easier to visualize. We'll just call this one sub. Smaller, and hopefully we're entirely on the same page now. I guess we'll have to make this a little bit smaller. Okay, so what we see here is we have all of our information completely available on the same page. So what we do now is, as before, we're going to enter our usage formula. So the usage is this, which is the shipments from plant A, the cost of plant A to plant B, times the number, plus the cost times the number, plus the cost times the number, plus the cost times the number. And we can skip the other 8 because they're all 0 and the ultimate end goal will be 0. So we hit enter. It will be 0 now because we haven't shipped anything yet. We repeat, the cost times the number, plus cost times the number, plus cost times number, plus cost times the number. A third time. And we've completed our first 3 constraint equations. We repeat it again with only the ones where 1 is a possibility. If it's 0, we can pretty much ignore it because 0 times anything is clearly 0. All we have to do is make sure they align with each other. That's what we've done here. So if we see here, plant A, city A, plant A, city A, plant B, city A, plant B, city A, plant C, city A, plant C, city A. We hit enter, 0. Repeat again. Plant A, city B, A, city B, plus B, city B, B, city B, plus C, city B, C, city B. One more time. AC, AC, plus BC, BC, plus CC, CC. Final time, AD, AD, plus BD, BD, plus CD, That's what we've done to complete our constraint equation. Now the final thing we have to do, for as always, we go to our solver bar. We come over here. Now we have to sum the total of all the cost per route times the total routes. So here, 8 times the number of times we run that route, plus 6 times the number of times we run that route, plus 10 times the number of times we run that route, plus 9 times the number of times we run that route, plus 4 times the number of times we run that route, plus 8 times the number of times we run that route, plus 12 times the number of times we run that route, plus 9 times the number of times we run that route, plus 14 times the number of times we run that route, plus 9 times the number of times we run that route, plus 16 times the number of times we run that route, plus 5 times the number of times we run that route. So this is multiplied all 12 possible route costs times the number of times we ran all 12 routes. So we hit enter, and we are now ready to enter the final stage of the problem, our usage of the data bar. So let's go up, click right here, over to the solver, and now we can begin entering our data. Our objective function is to determine shipping costs. We see that right here. It's a minimization situation. The routes that are going to change are B15 to B26. We don't have to enter them manually. We just drag right here. This is where the computer will run permutations and attempt to solve, determine what our optimal solution might be in this situation. We're going to make it SP simplex LP because we always do. And now we have to add our constraints. Looking at our constraints, we see less than or equal to, less than or equal to, less than or equal to. So all three of those can be entered as a single constraint. The computer is able to read that information. So we're going to add it here. Constraint number 1 must be less than or equal to these three. Sorry, I made a quick type mistake. So cell reference, these three columns, the constraints, must be less than or equal to these three. That's our first constraint. The computer is able to extrapolate and follow the patterns we established. So we add that. And our second constraint, these 4 must be less than or equal to these 4. And we can drag and drop because, again, it's always greater than or equal to. We add that now. So we now have 2, which represents actually 7 constraints. All of our formula have been entered on the spreadsheet. All of our key information is contained in the solver, simplex LP. We hit solve, and we allow the computer to run permutations of the 9 empty cells, which will dictate how many times we run each route. So we hit solve now, something happened. Give me 1 second. I'll be right back. Oh, I figured out what the mistake was. It was a very simple mistake. So let's revisit the solver function. The reason everything is 0 is because I made one small mistake. If you see here, the last one has to be greater than or equal to. I left it as less than or equal to. So let's change our constraints. Let's delete this constraint and we'll add it again. So cell reference 1, 2, 3, 4 here must be greater than or equal to these 4 over here. So we add that, we press OK. Now we have our reverse signed must be less than or equal to, must be greater than or equal to. We hit solve. All constraints and optimality conditions are satisfied. We hit OK, and we examine our results. And we see that from plant A to city B, we ship 5 units. From plant A to city C, 30 units. From plant A, so that means 35 units are being shipped from plant A, which is acceptable. That's the maximum they have available. We see that 45 units are being sent from plant B to city A. City A requires 45. That satisfies that. But plant B is also sending another 5 units. They have 50 units to send. This is still optimized. Finally, plant C to city B is 10 units. So city B now has a total of 20 units, which is how much they require. 5 from plant A, 5 from plant B, 10 from plant C. And plant C will send all 30 units to city D. All constraints are optimized, or all constraints are obeyed, and our optimization has been found with $790 total. That is our minimum possible shipping cost. Thank you everyone for listening. When we resume, we're going to look at something new. See you soon.